Okay, so just a show of hands, how many people had difficulty with the last page of the...
I didn't have too much difficulty. It just took me a while to try to figure out what exactly was expected.
All right, one more time. You had trouble with the last page, the last two questions. Okay, so this was what we worked on Wednesday. We spent most of the class Wednesday doing. We even got a little behind because we took extra time to do it. So what I'm going to do is, I think these two also gave the most difficulty, and I think they're the same type of question. So I'm going to go over these from the My Stat Lab, and then I'll let you turn, if you want more time, I'll let you turn this on Wednesday, okay? This, if you want to revise it, if you want to change your answers. But before we do that, let me ask you this. How many people, if I asked, what are the two, you could confidently answer this question, what are the two values that characterize or define a distribution? Who could confidently answer that question? What are the two values that characterize or define a distribution? Raise your hand if you could confidently answer that question. Everybody needs to raise their hand. So what do you think? The mean, here, ready? The mean and the standard deviation. So everyone needed to raise their, everyone at this point should have, but didn't. So that's where you need to address this. The two values that characterize a distribution, that tell us what the distribution is like, are the mean and the standard deviation. What is the mean? What does that number mean? This is another question we should all be able to answer. What is the mean about? Okay, what's that? So what's that? Okay, it's the average. What's that? What does it tell us? What does that number mean? The average. Okay, but that's how you calculate it. That doesn't tell it what it means. What does the average mean?
It's like a typical representation of the thing.
The data values. Yeah, that's really well said. It's like a typical representation because it gives us the what about the data? What does it give us about the data? You said it before, and then you changed the formula.
Oh, yeah,
the middle, the center. Just stop right there. Don't say anymore. It's the middle of the data. It's the middle of all the data values. It's like that, and it gives you an indication of what a typical data value is like, right? So what's going to be the mean length of pencils in inches? It's not going to be 100 inches, right? It's not going to be 1,000 inches. What's the mean length of pencils in inches? Just guess. 7, 6, 10, something like that. Not 1. The mean won't be 1 inch. The mean won't be 20 inches for pencils, right? So when we say the mean of a pencil is 8.2 inches, we're saying the mean length, we're saying that's what a typical pencil is like, right? Okay, what about the standard deviation? So somebody knew. What does this number tell us about the data? What does this number, standard deviation, tell us? How far away it is from zero. How far what is away from the mean? So that number tells us what about the data set? I think I'm asking the right questions here.
How far a sample is away from the mean?
How far a sample is away from the mean. So, okay, distance, this has to do with distance from the mean. Okay, it has to do with distance from the mean. Distance between data values. But just in general, so not what is the number, but what does the number tell us? What does it tell us? A low standard deviation versus a high standard deviation. Do you know?
The distance away from the mean.
Consistent. Okay, so now we're getting at consistency, or yeah, go ahead.
The spread.
How spread out the data is. A high standard deviation means the data is what? Really spread out. And so what will the curve be like? Low and flat, right? Because we've got a lot of data spread out, but then, so in any given place, there's not a lot of it, right? So it's low. And then what about if the standard deviation is really small? All the values are close into the mean. So what does our curve look like? Real tall and skinny because we have all this data close to the mean, so that the frequency is real high near the mean. Okay, so those are real basic things you have to remember. So so this is important, especially important now that we're doing this stuff, because we have two distributions that are going on at the same time in these problems. There's the original data distribution, which has a mean and a standard deviation, and then what are we doing? We're taking these samples, and we've got the mean of every sample, and we make a new distribution out of those means. So we have two of these distributions that are kind of happening at the same time in these questions, so we have to keep track of that. Okay, so good discussion. So I hope this is helping. Okay, so what are the two different? We have the population, and then the sampling distribution of means. So the population is just where we have all the data values, and we find the average, and we find the standard deviation just of the single data values, right? And so for this problem, okay, so for this problem, so like I said, we have the population, and then the sampling distribution of means. And what are the two values that characterize each of those distributions? Tell me your name in the corner. O'Day?
Yeah.
So what are the two values that characterize a distribution? The mean and the standard deviation, right? So we're going to have a population mean and a population standard deviation. And then eventually we're going to take samples, and we're going to have the mean of the means of those samples and the standard deviation of the means of those samples, and that's a new distribution. Okay, so do we know any of this information right now? So that's two sets of values that we're going to have.
Yes. Mean, and we know the standard deviation.
Of which? The population or the sampling distribution?
The population.
The population. What's the mean of the population?
1.5 kilograms.
For what? Brain weights. Brain weights. And that tells us typical brain weight, right? Typical brain weight, or the center of all the data. And the standard deviation is?
0.12 kilograms.
0.12, which is an indication of?
The standard deviation.
What is an indication of what? How spread out the data is. So what's your sense of this? Is there a wide variety of brain weights for men, or is it pretty narrow? 0.12 kilograms. Plus or minus 0.12 kilograms accounts for 2/3, 68% of all brain weights. Remember that? So you go out one standard deviation, you go up to 1.62 and down to 1. So from 1.38 to 1.62 is 2/3 of all males have that brain weight. Okay. All right. So the sample mean. So how do we get then? We're going to take the means of size 3. We're going to take all samples of size 3 and take all those means from those samples and take the mean of that, the mean of those means. What's that going to be? It's going to be the same, right? It's going to be the same. If you take all samples of a certain size, find their means, and take the means of all those means, you're going to get the same mean as the population. Okay? So here in part A, they're asking now about the sampling distribution, right? Okay, sample standard deviation. So now they're asking about for the distribution of means, what's the standard deviation for the distribution of means? And there we have a formula for that, right? Is it going to be less or more than this? Is it going to be less or more than this? Less, right? Because when you start taking samples and take the means, those are going to tend to be closer to the mean. So it's going to be less by dividing by square root of 3. Okay, someone have that in their calculator?
0.069.
Thank you. What does it want? 4 decimal. It wants one more decimal place.
3.069.
Thank you. Sweet. Okay. All right. What about now? We're going to take means of distribution sample means for samples of size 12. And then we're going to take the mean of all those samples and take the mean of all those means. What will that be? So this problem, we've got 3 distributions to keep track of so far, right? We've got the population. We've got the distribution when sample size is 3, distribution of means. And then we have the distribution of means when the sample size is 12. So now we're talking about a third one. So this is for n equals, this one was for n equals 3. And now they want another one for n equals 12. What's the mean of the means going to be? 1.5. What's the standard deviation going to be? 0.12. Right. 4 decimal places. Oh no, so we got the 1.5 again. 0.346. Awesome. Are we good? So we're keeping track of 3 distributions now, right? And every time we make the sample size bigger and we take the mean, those means will be closer and closer to 1.5. So look how small the standard deviation is now for samples of size 12. It's really small. And it makes sense because when you take a bigger sample, the tendency will to get a more exact mean. You won't get all large brain weights, 12 large brain weights that'll take you like too big, or all 12 small ones. You're going to get a mix of brain weights that will average closer to the mean when you take bigger and bigger samples. Is that the whole thing? Three parts remaining. Okay, so then they want us to choose, start the graph, for 12 and 3.
It's going to be A.
What's the difference between them? Oh, I see. Okay, so right. So we got all 3 to keep track of. So which one has the smallest standard deviation? 12, and the biggest standard deviation? Population. Population will have the biggest standard deviation, and then as soon as you start taking samples, the means of the samples will have smaller and smaller standard deviations for larger and larger samples. So Paul is suggesting A. You guys agree? Yep. Determine the percentage of all samples of 3 men that have a mean brain within 0.1 kilograms of the population brain weight of 1.5. So, which distribution they're asking us to talk about or to work with? 1, 2, or 3? Number 2, the one with n equals 3. So we're going to use this mean and this standard deviation, and we need to get a percentage of samples that have a certain mean. What's this about? How are we going to do this? Z-scores, right? We've got a standard distribution. So Z-scores are what are the link to getting percents of the data or probabilities of picking something in the data. So we want to be within 0.1 kilograms. So let's draw a picture here. So here's 1.5. So we're really looking for between what and what? Good, 1.4 and 1.6. So we want the percentage of all the means, or percentage of all samples that have a mean between 1.4 and 1.6. And how are we going to do that? A general strategy. How are we going to get that percentage that lies between 1.4 and 1.6? So this is back from,
You find the z-score of everything
Right.
left of 1.4 and subtract it from the z-score of 1.6.
nice, okay. So we're going to get the z-score for 1.6. It's just asking how many standard deviations 1.6 is above 1.5 and for below. So how do we get the z-score for 1.6? It's going to be 1.6 minus 1.5 over. Do we remember what we found for that? 0.06693.
693.
Because I'm zoomed in, my pen is kind of hard to write with. And then z of 1.4. And these are our adjusted, right? We took these values in our distribution and they're adjusted to the standard normal distribution so that we can use the table. Okay, what'd you get for the z-score for 0.1 divided by 0.0693? The z-score.
1.443.
And then is this negative 1.443? It should be just the opposite, right? If this is 1.443, this should be negative 1. Is that right? Negative 1.443. And now you go to your chart. And we're going to get the chart's going to give us all the area to the left of 1.443 and all the area to the left of negative 1.443. And like Mackenzie said very well, you're going to subtract all this area to the left of negative 1.443 from all the area to the left of 1.443. So anyone got what's the area for z-score of 1.44 from the table? 0.9251. And then what about to the left of negative 1.44? 0.0749. Subtract, and that gives us the area between, which is 0.8502. Rounded to 2 decimal places, right? 0.85.
They want a percent.
Thank you. So just 85. So 85.02. We got there eventually. Teamwork. All right, so they want it as a percent, rounded 2 decimal places. That means we take all 4 values that we got from the table. Okay, so before we do this one, now let's think about this. Is this going to be a bigger percent or a smaller percent? So now we're taking samples of 12, and we're still going out 0.1 kilogram either side. Is that going to be a bigger percent of the means that fall in that range, or a smaller percent of means that fall in that range with the bigger sample size? Right, because look at the n equals 12 curve. We're still going to go out the same amount, 0.1 on either side. We're going to get almost all of the data now. Almost all the data, all the samples are going to have means between 1.4 and 1.6 because with n equals 12, all that data, all those means are crunched in around the mean more, right? So we won't do that one for time's sake. But so those last 2 questions on the written take-home quiz are the same as this, except they kind of just start you off with this question. It's just they're asking question D without taking you through all the steps. Okay, so they're really asking a question in those last 2 problems, just like question D. So that's why I set you up with questions A and B myself to kind of get your mind oriented. You want to do that. So you're gonna write the population mean and standard deviation, and then the sampling distributions of means that they're referring to in that problem, whatever the sample size is. You have those 2 distributions, and then you're going to decide which one you're going to use to answer this percentage question. If they want a percentage of all samples whose means are in a certain range, then you're going to use your sampling distribution means. So let's take, if you want to take till Wednesday if you want to revise that or keep working on that. And if you got it done, you're happy with it, then you can just hold on to it and bring it again Wednesday and turn it in, okay? Any questions on this? Please.
Not about this,
Yeah.
but about something else that's on the.
Okay, one more question and then, yep.
I don't really understand how to determine which sort of graph you would is appropriate for
Yeah.
different scenarios.
Okay, so let's just talk, is there one you want to talk about?
Well, just for example, or which one was it? When you, if you were to pick a random sample of cars,
Okay.
of, years of
Right.
cars off of university, I put that would be just
So-
that it would be the normal graph because that would likely be normally distributed.
So when you do these, you want to start by writing the values of the variable along here. So what numbers, right? So on the horizontal axis is values of the variable. And then the vertical height is frequency, right? So how would we have to number our graph here to start talking about what that distribution would look like?
Years.
Right. So where do you want to start?
Well,
Do you,
I don't know, because
do we want to start at 2000?
well, probably
No.
not.
Okay, so where do you want to start?
Because you're gonna have some students who are gonna be driving old cars.
Yeah, sure. So do we want to say 1900? Okay, so okay, but see, so is what I'm saying. You know where we should start about, and that's fine. It doesn't have to be perfect.
But
So
I kind of assumed that most cars would fall kind of within.
just go with me here. Where do we want to start? What year do we want to start?
I don't know.
Yeah, 1900 and not 2000. So 1950, 1970, it doesn't matter. So I'll say 1960. Okay, and then we'll have 1980, and then we'll have 2000, and then we'll have 20. Are there 2017 cars out yet? No, just 2016. Those come out in the summer, right? 2017? Okay. So now imagine you're going to notice the cars going by and take a random sample. What do you think will be the most frequent? Do you think the most frequent will be in the middle here, 1990s, so it'll be normally distributed? No. Where will the most frequent number cars be?
Maybe between 2000.
Over here. You're going to see cars that are 5 to 10 years old, mostly, or 0 to 10 years old. And you, like you said, you may see a couple older ones. So what kind of skew is that? Left skew. Does that help? Put the numbers, get a scale for your variable, and then you have something to think about, you see, in terms of frequency. So this would definitely be right skew, left skew, right? Because most of the data will be the large values, recent years, right? Recent years. In fact, I probably didn't do this great. I'll do it a little better. I mean, what would you say that, most of them are going to be 2008 maybe and on. So maybe like this. Okay, so I hope that helps. Okay, great. Okay, let's press on. So you had a couple questions at the end, and there was high success. So I'm just going to go in terms of these confidence intervals. So that's good. We'll just go through it. So what is a confidence interval? Confidence interval is an interval of numbers obtained from a point estimate of a parameter. And we've talked about a point estimate. The one type of point estimate we've talked about is you take a sample and you get the mean of the sample, and that's a point estimate of what? The mean of what? No, that it is the mean of the sample. So it's not an estimate of the mean of the sample. What do we use samples to estimate about? This is what statistics is all about. Inferential statistics. Remember at the beginning of the course? Inferential statistics. We take information about a sample and we try to generalize to the population. This is a huge part of statistics. So a point estimate would be take the, so don't, kind of really make sure you're listening, and because what I'm talking about is not what you would be writing if you're copying down the words on the screen. So make sure you're staying with me. A point estimate is like you take the mean of a sample, and that we use that to estimate the mean of the population. Inferential statistics. Okay, so will the mean of the sample be the mean of the population? Will it be the mean of the population? Will we get it? Will it be exactly the mean of the population? Think about our sampling distribution, right? We take lots of different samples. Do we get the same mean every time? When we take samples, do we get the same mean? No, we get a distribution of means, right? That's what we just worked on the last 2 days, right? We get a distribution of means. And the distribution of those means, the mean of those means will be the population mean. So any one sample will not give us the population mean, or if it does, that would be very rare. It will give us an estimate of the population mean. And then the distribution of the means will give us a mean that is the population mean. Okay? So if we just have one sample, which is very common, you're just going to get one sample and you want to make an inference about the population, that sample mean will not be the population mean, but it'll be our best guess, right? It'll be because it's what we've got. It's what we've got. So what we do is we make what's called a confidence interval. So we take that point estimate and we make an interval around it such that we say we're a certain level of confidence that the population mean is in that interval. Because the mean of the sample will most likely not be the mean of the population, but we can make an interval and say we're 90% sure, we're 95% sure that the population mean falls in this interval around our point estimate. Okay, so that's the idea of a confidence interval. So let's look at an example here. So here's prices of new mobile homes. Here's a sample of 36 mobile homes, and there's the mean of this one sample, 63.28 is the mean of our sample. And they're saying that the population standard deviation is 7.2 thousand. So the mean is 63.28 thousand. And what does the mean give us again? What does that number mean? Right, a typical mobile home, or the center of all the data, right? If you're going to pay for a mobile home, it's what you'd expect to pay, right? What you'd expect to pay. The 7.2 thousand is an indication of how spread out. How spread out. Like, so it's telling us, are all mobile homes really close to 63,000, or are they all over the map? That's what that number is telling us. So there's a pretty good spread, right? So from 55 to 70,000, that's a $15,000. We get about 2/3 of mobile homes, 68% of mobile homes, right? Okay, so it says identify the distribution of the means, the sampling distribution of means for a sample size of 36. And now we all know what that means to identify a distribution. What does it mean to identify a distribution? Madison. The mean and the standard deviation. What is the mean of the means? 63 points. So we do this. The mean of the means is 63.28. And the standard deviation of the means is it 7.2? Good. 7.2 divided by the square root of 36. 1.2 thousand. Okay? So we take samples of size 36. Those means are going to be really tight around 63, right? It has a small standard deviation because all those means of samples of size 36 are going to be really close to that $63,000 mark. Okay, so a 95.44% confidence interval, this number should seem familiar. What is that about? 2 standard deviations from the mean. Okay, good. So we've got our distribution of means And so we want to go 2 standard deviations up from this and 2 standard deviations down from this. And that will be a confidence interval of 95.44%, meaning we'd be about 95% confident that the population mean lies in that interval. So how are we going to get that range? So here's 63.28. What are we going to do? How do we get the top of the range and the bottom of the range? What are we going to do?
So you're going to do 1.2 times 2 to get 2 standard deviations.
Right.
And you're going to add that to 63.28.
Good.
And that's going to give your right, or your
Yep.
right side of the interval. And then you're going to do the same thing minus 1.2 times 2, so 2.4.
Yep.
And that's gonna give you your left side.
So 2 standard deviations is 2.4. Are we good with that? So we're going to go, if we're going up 2 standard deviations, we're going to go up from 63.28 by 2.4. And that is 65.68. And then down 60. 60.88, thanks. So what does this interval again mean? From 60.88 thousand to 65.68 thousand? What are we saying about that? Okay. That's a different question. That's not the question we're asking here. So this is no longer percent of the data, but it is, but we're using it to talk about inferring. We're talking to infer about the population mean. Heather, is that a hand?
We're 95% certain that 95% of the data falls within that range?
Nope.
Not the data, but the mean.
So, say it again.
Not the data, but the mean.
What mean?
The mean from the standard deviation. Or the population.
The population mean, right? This is all information from what? From a sample of size 36. And our goal is to find out about what? The population. We're taking this sample of size 30. This is statistics, right? You get a sample of a huge population, then you try to figure out stuff about the population. So this is it. So we got the mean of the sample, and that's our best guess at what the population mean is. Is it the population mean? 63.28? Is it the population mean?
No.
Very unlikely. Is it close? Size 36, that's a big sample. It's close. It's pretty close, right? It'd be very unlikely if the population mean wasn't close to that, because we have a big sample, right? Okay, so but now we want to say, okay, we can be 95% sure that the actual population mean is between like 60 and 65, or 61 and 66,000. All right? So there's still a chance that the population mean lies outside of this range, but only a 5% chance. So suppose we kept taking samples of size 36 over and over again. So 95, that's like 19 out of 20, right? That's like 95% is like 19 out of 20 times. So 19 times out of 20 that we make a confidence interval like this, the population mean will fall in it, and maybe about 1 time out of 20, we'll get an interval where the population mean is outside of it. So this is what that next slide shows. Because 95% is about 19 out of 20. So here is $20 samples of size 36, and here's the means that we got. Okay, and then we set up the same. We set up the confidence interval just like we did. And so here's all those confidence intervals. And so now they're telling us that the actual mean is 65. The population mean is actually 65. And what do you notice? 19 of those confidence intervals. So the green dots are the point estimates, the mean of each sample, and then the black line is the confidence interval for that sample. So one of those out of the 20, one sample was extraordinarily large. Like, so on the average, all those that they sampled were really large compared to the population. So that particular one did not give us, that interval did not give us, the population mean did not fit in that fall in that interval. But in 19 out of 20 of them, the population mean of 65 fell in the interval. Does that make sense? So this is the idea of a confidence interval. So normally you would just have one sample. You would just have one sample. The green dot would be your best guess at the population mean. And then the interval would give you some percent of confidence that your population mean is in that interval.
67, 73.
Which was the one that we did? Is the one that we did on here?
60,
What was our mean?
I mean,
65, 28? 63? Is it one of those?
63, 28.
So let's draw ours. So ours was what? 63, 28. So something like this. And what was our high? 60 what? 60, just made it, right? Just made it. And the low was? Something's wrong. Tell me again. What was the point estimate that we just did, the previous screen? Anyone write it down?
63.28.
63.28. Okay, that's right here.
Low estimate was 60.88.
60.88. So I must have gotten the high wrong. I must have heard the high wrong. 60.88. Okay. And the high was?
65.68.
68. Okay, up here. That's better. So this was the one we got. Our point estimate was just over 63. We got an interval, and ours contains the population mean, which was 65. Okay, does it make sense? Any questions?
So you only use confidence intervals and ranges to find the mean?
We're trying to estimate, we're trying to get a picture of the population mean from a sample. So the point estimate is our best guess, and then the range gives us an interval with which we're some degree of confidence that the population mean is in that interval. Yeah, but it's all about trying to pinpoint the population mean. This is the idea of inferential statistics. Figuring out stuff about the population based on a sample. Did I answer it? Okay, let's just press on here. Okay, so we're going to relate the same thing. So this isn't new. We're just going to relate it back to the alpha thing. Do you remember the alpha thing? Let's review that. So remember what Z alpha was. Do you remember that? What was Z alpha? So first of all, is it a percentage or a Z-score? It's a Z-score. For which what? What did the alpha mean? Remember? Yeah, it was kind of the opposite. It's kind of counter to what the table gives, right? The table gives all areas to the left, and this alpha was area to the right. So the Z alpha is the Z-score for which the area under the curve, or percentage, to the right of Z is alpha. So what would Z of 0.3 mean? So as an example, z of 0.3 would be the z-score for what? Everything to the right of 0.3. Not quite. What is 0.3 here? What does 0.3 mean? Is 0.3 a z-score? So what does the 0.3 mean? Area to the right, right? So the area to the right. So this is the z-score. So if you looked in the table, you're going to look, where are you going to look in the table to find this z-score? You're going to go into the table first, right? You're trying to figure out, you're going to use the table backwards, right? So what are you going to look in the table to find z of 0.3? What number in the table are you going to look at? 0.7. Remember there are four decimal places, right? 0, 0, 0. So you're going to go into the table and you're going to look for an area of 0.7000. Because that's going to be 70% lies to the left or 30% lies to the right. And that's what we want. So it's going to be like this. 0.25 is the closest one. So a z-score of 0.25. That's z of 0.3 because 30% of the data lies to the right and 70% of the 0.52. That sounds better. 0.525? 0? Oh, between. Okay, so you're doing between. So where's the area of 0.3 again? To the right. This area here is 0.3. And this area here is 0.7. So this is then z alpha, where alpha is 0.3. Z.3 is 0.525. So now they're taking this, we're going to use this Z alpha notation along with these confidence intervals. We're going to kind of combine those two ideas together. Okay? So if it's a 90% confidence interval, did you get it?
Yeah, I was just looking for the whole, should be.
They're kind of it's called extrapolating. They're finding the one in between, right? Okay. So if it's a 90% confidence interval, so that means all this shaded region here is 90%. So what percent do we have on outside of the interval? Like say on the right, so on the right side and the left side, what percent do we have? So 10. Are they both 10% or is it 10% total? 10% total on either side. So what percent? So that means 10% total outside. So what percent then would be to the right of this? So this z-score right here. So we're doing 90%. Let me change it. We're doing 90% confidence interval. 0.900 lies in our confidence interval. So then what percentage would I have here and what percentage would I have here? It's 90%. 5% each, right? Or 0.05. 0.05 on this side and 0.05 on this side. That would make the 10% total lying outside of our confidence interval, right? That means 0.055% to the right, which would mean, what was our alpha value then? What's our alpha value? For this z-score right here, what alpha value are we talking about for a 90% confidence interval? So what percent of the data is here? 5%. So it's z of what? 0.05. And to do z of 0.05, what in the table, where are we going to look? So what percent are we going to look at? 0.9500. And that will be the z-score. That will be the right side of our 90% confidence interval. Did you track along all that down there? So let's do it again. 90% confidence interval means a total of 10% outside of the confidence interval. It means 5% on each side, so 5% to the right. So that's our alpha. So z of 0.05 is what we want. That will give us the z-score for a 90% confidence interval, or the top limit. Okay, so then to do z of 0.05, we're going to go in and look for an area of 95%, right? Because all this is going to be 95%. And what is that? Z, what is z?
It's like 1.64 and 1.65.
So 1.64, we're extrapolating again, 1.645. 1.645. So for a 90% confidence interval, the z-score will be plus 1.645, and then by symmetry, what will the z-score down here be? It's centered right on the mean, right? So if 5% above is this z-score, then 5% below is going to be negative 1.645. Okay, so, but because it's a z-score, it's going to be the same for any time you do a 90% confidence interval. You will always use these z-scores. Why? Because that's the standard. The z-scores are the standard normal, right? No matter what distribution you have, if you change it to z-scores, the z-scores are kind of our like home base, or our like reference point. So whenever you have a 90% confidence interval, it will always be these z-scores. You don't have to do this again. We don't have to do those. We don't have to go through this again. Okay, so I want you to go through this process for do it for 95%. So find the z-scores for 95% and find the z-scores for 99%. So go through the same process that I just went through here across the bottom of the screen. And we want to get the z-scores for 95% and 99%, and then we never have to do that again. Whenever it asks for a 99% confidence interval, you're going to use the z-scores that you find right now. You never have to do that thing again. Yeah, Tabitha. Because z alpha, this means the area to the right. So we want 5% area to the right. But the table gives us areas to the left. So if it's 5% area to the right, so you go 95% to the left will be 5% to the right. So that's why we went into the table and said we want an area of 0.9500, like in the table, and then we're going out to the edges to find the z-score. Does that make sense? Here, when you do these z alpha things, you're using the table backwards. You're not taking a z-score to the table and finding an area. You're taking an area to the table and finding a z-score. So you're going into all the numbers. You're going to go in and find an area of 95%, because that's what it is. From here over is 95%. So you're going into the meat of the table. Does that make sense? That is the area. You're finding the z-score for a given area. So you're going into here, and you're looking for 0.95. And then you're going out to the edges of the table to find the corresponding z-score. So you're using the table opposite of how we used to. Right? We used to be given a z-score, and then we'd figure out the area. But now you have the area, so you're going into the 4-digit numbers. You're looking for 0.9500. And then working your way out to the edges behind the z-score. Does it make sense? I have so much work to return to you guys. Where's Caitlin? Is Caitlin here today? No, Caitlin? Compare with the people around you. Make sure you get the same thing.
That's what gets me confused when I'm trying to start you knew this, you could get back to 95.
Is Hunter here? Is Hunter here? Hunter? Yeah.
When you give us finals or midterms or finals and things like that, are you going to give us, show us the formulas or remember?
Whatever's appropriate. So yeah, if it's some things you have to remember, but other things aren't. It's whatever's appropriate, and I'll let you know ahead of time. Yeah. No, we'll just have them do it on Sunday nights now. Yeah. Is Daniel Green here today? Daniel Green? Yes,
Seems I used to do the pattern. Do patterns of doing I was going to do this year. It's strange.
All right. You guys good? So for 95% confidence interval, what did you get for the z-scores? What did you guys get? 1.96 and negative 1.96. Everyone get that? Anytime they ask you for a 95% confidence interval, you're going to use those values. Okay? You don't have to do that again. You don't have to do that again. 99% confidence interval. 2.575 and negative 2.575. Awesome. Okay. So let's move on here. We don't have to go through that, so we'll do examples. Okay, so here's ages and years of 50 randomly selected people in the civilian labor force. Assume a population standard deviation of 12.1 years. And then they're saying, this is going to help you find a mean. They're saying the sum of all this data, of all these 50, is going to be 1819. That's a little hint to help you find the mean of that data, okay? So we want to find 90% and 95% confidence intervals for the population, mean, age, mu. So we've got a sample, and we want to know something. We want to try to infer from the sample about the population. And we're going to do that with a point estimate and a confidence interval. Point estimate is like our best guess at the population mean, and then the confidence interval says we're this confident that the population mean lies in our interval. Think you can do it? Let me give you blue sheets. Okay, so we haven't done an example exactly like this, so I'm putting a little bit of responsibility on you here to kind of make sense of it. You're going to use what you just did to help you get that. So the confidence interval is going to be a range of ages, right? It's going to be a range of ages. So you're going to have the mean age, that'll be your point estimate, and then you're going to have a range of ages around that point estimate that are going to be where we think the population mean lies to that percent confidence. So you're going to have to think about that and think about how you're going to do that. But use what you just did. Use what you just did. Gina. We missed a day. That was two different days worth of points. So you missed a day of class. Yeah, if you had 10 out of 20 on the blue sheet, that means you missed a day of class. If that ever happens, it means that from a day you missed. You missed the points for the day because you didn't come. Is Christina here today? Christina?
That's me.
Okay. Because, is it making sense? Are you able to do it? You're, how'd you go, right? Jessica? Hello, Jessica? Jason?
The point estimate is when you take all of it and divide it.
Caitlin? Christopher's not here. Hunter? Not here. Jordan? Hunter, Christopher, Tabitha. Anybody get the 90% confidence interval? From what age to what age did you get? You don't get it? You guys get it? Send it up here. What did you get for the point estimate? How about let's do that first.
36.38.
36.38 years? Okay, anyone get the 90% confidence interval?
34.4.735 to 38.5.
Okay, 34.735 to
38.025.
38.025. Did anybody else get that? Okay, so we figured out the 90% confidence interval, right? So you took that many standard deviations. Yeah, no, so this is the standard deviation, right? 12.1. But then it's a, yeah, we better do this. Here, let me help you with this. This is a little bit tricky. Oh, but then, no, that's right, because did you divide by the square root of, you might have gotten it right. Did you divide this by the square root of, how many is this, 50? No, okay, that's the population standard deviation. Okay, let me just hand these out a little bit together. That's you, right?
Which formula are we using?
Tuesdays and Thursdays, 9:30 to 11:30. If you ever forget, it's on the syllabus. Jason, Alex, Tracy. Okay, no Jason. Okay, let's do this. So we got the mean, our point estimate you took 1819 over 50, and that was the mean of the sample, right? Sum up all the data values, divide by the number of data values. One more time. 36.38
36.38.
years. That's our point. That's our best guess at what the population mean is, right? That's all we've got. Is it the population mean? No. Or very unlikely. It might be exactly, but that would be very unlikely, okay? So maybe, but only a slight chance. Okay, so this is our point estimate of the population mean. So now we want a 90% confidence interval, but that's going to be based on a sample size of 50. So what we need is, then we need our sampling distribution data. Our sampling distribution has a mean of what and a standard deviation of what? 36.38.
And a sampling, I guess, standard deviation of 1.711.
And how'd you get that?
I did standard deviation divided by the square root of 50.
Good. And you said that was?
1.711.
1.711. Okay, so that's what our confidence interval is going to be based on. So what did we find for a 90% confidence interval? How many standard deviations above and below? Plus or minus? 1.645. So what? So we've got our point estimate, and we're going to go up 1.645 of these. Everyone, all right, everyone pay attention. Here's the key. We've got our point estimate of the population, and a 90% confidence interval means we're going to go up 1.645 standard deviations, but we're using a sample size of 50. So here's our standard deviation for samples of size 50. So we're going to go up 1.645 of these from that. And then we're going to go down 1.645 from the point estimate, 1.645 of these from the point estimate. So how do we do that calculation? Should make sense. So we're going to go, so we got our 36.38. How do we go, what calculation do we do to go up 1.645 of these? What will that be? Abigail's punching back there. What are you punching? Tell me.
1.645 times 1.711.
And then? Good. You see that? We want 1.645 standard deviations. What's our standard deviation? 1.711. So 1.645 of those above 36.38. And then 1.645 of those below 36.38. Does everyone know how to get that calculation then? So let's do it and see what you get. Everyone do that. As soon as you get this top one, give me a number. What is it? 39.19? Did somebody else get that? Everyone should be able to get that number. Make sure you understand what's going on. And then we're going to go down that same amount.
33.57.
So, who can fully interpret what we just found when I'm putting a cloud around? Here. Fully interpret what that thing means that I put a cloud around. Naomi, want to try?
90% between 34 and 40.
Is it 90% of some amount of data? Is that what we're talking about here?
There's 90%
90%
confidence.
confidence of what? We have 90% confidence of what?
Population mean.
Did the population mean? is in that interval. We're 90% sure that the population mean is between 33.57 and 39.19. That's what we just found. And that was based on a sample size of 50. If we had a smaller sample size, what would happen to this confidence interval? Would it get smaller or would it get bigger? If we wanted the same amount of confidence and we had a smaller sample size, would that make us more confident or less confident? Yeah, so 90% would be a smaller confidence interval, right? If we had a smaller. Yeah, Tabitha. So what did you do? You're starting from 36.38 and you want to go 1.645. No, of these, right? We want 1.645 of these. So that means we're going to, like if you wanted 2 of these, what would you do? You wouldn't add 2 plus this. If you wanted 2 of these, what would you do? You'd multiply by 2, right? If you wanted 2 1.71s, you'd do 2 times that. So we want 1.645 of these. So you're going to multiply. I didn't round to 2. I was using an example. If you wanted 4 of these, what would you? If you wanted 4 1.711s, what would you do? Times 4. So now, what do we want? We want 1.645 of those. So you're going to do times. You're going to do times. Right, 1.645 of those. So that's multiplication, and then that result greater than 36.38. Did you get 39.19 this time? Okay. Okay, so let's do make sure you get this in your notes, but then also make sure do the 95% confidence interval on your blue sheet. Okay. So you're going to use the same sampling distribution. Same sampling distribution, but now instead of a 90% confidence interval, we want to be 95% sure. Is that going to be a bigger range or a smaller range to be 95% sure? We want to be more sure.
Would it be smaller?
We want to be more sure that the population mean is in our range. It's got to be bigger. We want to be more sure that the population mean falls in the range. So it's going to be bigger, and that's because you got a bigger z-score, right?
But if you're 95%, like you have 95% more confidence, then wouldn't you have?
To be more confident, you need a bigger interval for the mean to lie in that.
So it's not necessarily getting more precise. It's just.
So which one is more precise?
Bigger so that you have a bigger chance.
Yeah, we've got. If we want to be more and more confident that our population mean lies in the range, we got to make the range bigger and bigger. Then we're more confident that the population mean falls in our range. So do the 95% for your blue sheet.